Until recently, the way magnetic materials have been switched was when you change the north and south pole orientation, you apply a magnetic field. I understand that recently you've been working on a method to switch magnetic poles without using a magnetic field as traditional. Could you tell us something about that, Bob?
Certainly. Yeah, that's really been well, all these have been rather fun activities, but this in particular was rather unexpected. Uh, that, so one of the things that the areas that is of high interest right now certainly in the recording industry is how to how to get higher and higher storage density. One problem with doing that is as you as you try to magnetize your disk, that local region, say perpendicular, that would be your 1 in binary encoding, or opposite 0 in binary encoding. In order to do that switching, you had to apply a magnetic field in the direction you wanted to switch it to. So if it was that local region's magnetized up, you want to switch it down, you'd have to apply a field perpendicular, which would cause it to switch. Well, imagine the effect of that magnetic field on the region below where you have it magnetized. Well, it's going to cause those regions, if it's magnetizable, also to switch. And that's one of the reasons you can't, or up until recently, you could not get 3-dimensional storage on your material. It was all 2-dimensional. It's limited to putting things on the plane of your hard disk or tape or whatever, but you couldn't put things underneath it easily that you could cause to switch with a magnetic field up and down, because if you used a magnetic field from outside, it would switch just to both the top and the bottom at the same time. So there's always been an interest in somehow being able to switch this magnetization from up to down without using a magnetic field. And one way that people have come up with in recent times was to use the fact that there's a spin orbit coupling. That is, there's a coupling between the trajectory an electron takes and the magnetic spin on that electron. And it's what's responsible for the Hall effect, for instance, to create voltages. If you apply a magnetic field perpendicular to the direction of an electric current, then you can impose an electric potential in the other mutually orthogonal direction. Well, so that comes about from this spin orbit coupling. One thought was to try to use that somehow to switch the magnetic spins in the material up to down, and it's been largely unsuccessful by taking advantage of this spin orbit coupling. But what was predicted here a while back is if you had an anisotropy in your material, so that if you, for instance, had a heavy metal on top of your ferromagnet, the heavy metal has lots of spin orbit coupling occurring in it, and whereas less so in the ferromagnet. But if you put an electric current along this sandwich, or not sandwich, but this bilayer, then the coupling of electrons at that interface could well exert some sort of torque on the magnetization of these spins in the ferromagnet. And in fact, people found that if you applied a magnetic field in the same direction as the electron current, in fact, in some cases, if you pulsed it, you could get switching from, if you had the material perpendicularly magnetized from up to down. And the switching occurs because with a field this way, then the spins which are up are going to precess around this field. And if you pulse it only so long enough that the spin is now down when you take that field off, now it's in the down position, it will stay there. That was the idea, but still requires a field. The effectiveness of this spin-orbit coupling is proportional to what is known as the spin-Hall angle. And this is a quantum mechanical effect, but it tells you which way spins are going to be moving. So if you actually have an electron current going down through this ferromagnet and a heavy metal on top, as I described before, then what happens, the perpendicular to the direction of motion of the electron and the direction of spin of the electron, it will cause a motion of those electrons in that third mutually perpendicular direction. So if the current's going along the plane of this film and the sample is magnetized upwards, then if electrons which have spin in the plane but perpendicular to the direction of motion will cause electrons with that spin state to actually move up or down, depending upon whether the current's going this way or the other way. So it causes large number of electrons to move up in this sample up to the boundary separating the heavy metal from the ferromagnet. And in fact, if you have a large enough spins in this one direction, it can cause a torque on the ferromagnetic spins that cause it to switch over. And similarly back. Well, if you just had a single heavy metal, it apparently doesn't work really well because you can bring the spins down, but you can't continue to reverse them to the other direction. So Chuling Chen from Johns Hopkins University and a couple of his students came to us and wanted to know if we could use our imaging, our domain imaging tool, to look at it perpendicular to see if we get switching definitively as we put electric current through it. And so, of course, we felt this would be a good tool to use because then you could tell whether it's definitively switched from up or down and vice versa. But what they did something a little different. They made a sample which had a nice heavy metal like platinum on top of the ferromagnet. In this case, it was an alloy of cobalt, iron, and boron, which is known for the thickness of it to give perpendicularly magnetized material. And by putting this platinum or heavy metal on top, you would get this spin orbit coupling and scattering. It would cause electrons with a certain spin state to migrate up and the other opposite going down and causes torque. But then they took a second heavy metal, tungsten, which does the same thing. It causes some electrons to move up and some electrons to move down, but it causes electrons to move in opposite directions than the platinum does. So the idea was if you set up basically a spin current going up and a similar spin current going down in these two heavy metals, they should cancel each other and we would not see any switching at all, but it would be of use to examine if there's any effect on the magnetization of that cobalt, iron, boron. So that's what we set out to do. And lo and behold, we found that if we set up that sort of current, then in fact, we can cause switching. And we have a nice video, which we may show later on, which shows the switching, where it goes from a dark region to a brighter region when we pulse the current in one direction. And then we come back and pulse it in the opposite direction. It changes from a very light region to a dark region, showing that we've gotten magnetization reversal from up to down and then back up at will. And this is without using any magnetic fields at all. So this is a rather exciting finding. I have to confess, we still don't really understand why it's happening. But it's a real effect, and we can control this at will. And so there are a lot of people now looking further on at this, I actually have reduced my activity in that particular area, primarily because just after we published our results, I decided that it was time actually for me to retire officially from government service. And so I don't really have as much access to equipment as I used to, but it's really an exciting area that I fully expect we'll see some outcomes in commercial products in the future. What's also kind of interesting about this whole area is this whole area of spin orbit coupling is something that my father showed in his PhD thesis actually existed. Up until then, there have been theories that there was an interaction between the spin of an electron and the trajectory it took, or its orbit, but nobody had really shown outside of experimental air, that it actually existed. And that was my father's PhD thesis. They didn't call it spin orbit coupling in those days, but that's exactly what it was. And it showed that way outside experimental air that such a phenomena exists, never thinking about how it's going to be applied to present day electronics. So interesting aside.
So you've been doing cutting edge work your whole entire career. This is really right at the edge where we don't understand what the effect is, but the experiment shows that something is there to look at. So just amazing.
So I'm going to leave it up to people, smarter people like yourself, Matt, and others to come up with explanations of some of these things. Well, I mentioned it's always better to be lucky than really smart. So
I think that's a good time to change topics here. Don't
okay.
Your technical career has certainly shown your passion for the advancement of science. But I know that you've had other passions. And two of these are really not, they're not doing science yourself. It's service through professional societies and science and engineering education. And these are kind of sharing your experience with others and trying to make a difference in other ways. Why don't we start with the first one? When did you get involved in TMS, which I know is an organization you've spent a lot of time interacting with over the years? And why was it important when you started out working at doing service with TMS that you did it at that time?
So I got involved or became a member of TMS when I was actually an undergraduate student at MIT. And at that time, you could join both TMS as well as the American Society of Metals for the same student fee. And I did so partially because it was a way for me to meet my professors as well as other students, because the department at MIT would hold these informal gatherings, typically on Friday evening or late afternoon in the foundry there, where they had big furnaces for melting and casting things. And a number of the faculty would be there, as well as graduate students of them, in addition to the undergraduates. We were all invited. And it was a good way to kind of meet these other people, talk to your professors, as well as other members of the faculty informally without worrying about a problem set or something scholastic. And so that's why I joined. But I really didn't know much about the organizations at that time. And then later on, when I went to the University of Illinois in Champaign-Urbana, again in the materials science department, there actually was called metallurgy and mining department, because they had still a mining activity that was a very large part of the department many, many years beforehand, but had gotten much smaller by then. And I, again, stayed a member of this, a student chapter that they had there, although it was more a materials student chapter than specifically ASM or TMS at that time. And again, for a very small fee as a student, I was a member, but I really didn't take much participation in the society activities themselves, other than as a way, again, to meet other faculty members and students. It wasn't until, I guess, I had come back and joined, well, come back east and joined the National Bureau of Standards, that I started looking at it more seriously, partially because one of the members of this group that I helped form, Larry Bennett, said, you know, you really should get active in your professional society. Now, Larry was a member of the American Physical Society primarily, and he knew from his activities as a student there that how beneficial joining becoming active in your professional society was, in terms of primarily networking. So I did that. I kind of looked at the different committees in TMS, and it seemed to me the one that fit me best on the basis of my interest was the Chemistry and Physics of Materials Committee. This is a committee that transcends divisions in the TMS structure. It was part of both the Structural Materials Division and also the Electronic, Magnetic, and Photonic Materials Division, as it was called in those days. Now it's called the Functional Materials Division. But anyway, this committee transcended, and that made sense to me because they had applications to different TMS divisions. And so I applied to the chairman of this committee for joining, and after they looked through my CV and interest statement, they voted to have me join them. And that turned out to be very, very beneficial, because it, again, brought me into contact with a different community of people than I had met beforehand, many of whom are working in areas I'm not working in, and that enabled me to rely upon my previous education at MIT and the University of Illinois in terms of following what they were doing and recognize significance of what they were saying and doing. I began to organize symposia, and through doing that, I met more people. In fact, one of my advice to students or young professionals in general is, indeed, get involved with your professional society, whether it's TMS, ACERS, ASM, IEEE, APS, whatever. Get involved with that society as a way of networking and meeting other people. So what I found is, once I started to organize symposia, I would send out, of course, invitations to some of the people who had done some significant work that I had read papers from beforehand, and invite them to come to these symposia that I was putting together. And when they would come to the symposia, then I would had a good topic to break the ice and talking to them about. And that one thing led to the next, getting to know some of these people in more depth, and vice versa. While you're meeting them and hearing what they're doing, they're hearing about what you're doing. And so this is, and then of course they will talk about your work to other people. You'll talk about their work to other people. And it's a good way to spread information on the experimental results of yours, as well as that of others. And so I also then got involved in being the publication representative for this EMPMD division, and then I got involved in the programming committee. Programming committees, in particular, I think is one of the most important committees in TMS, because you're involved in putting together the program of each of the annual meetings, and I always thought of that as really a lot of fun, and of course a key output of being part of a professional society, because it gives you this venue for presenting your results and vice versa. And then I recall sitting down for lunch once with the present chairman of the EMPMD committee. That was Bruce Wessels at the time, and this was probably in the middle 90s. And also another fellow, Darrell Freer, who was from at Sandia, I think at that time, although he went into the semiconductor industry around that same period as well. And both of them were saying, you know, these symposia you're putting together are pretty interesting, and you know, you should think about taking a higher office in TMS, and an administrative thing. And I was not so interested at this point, because I spent my whole career, until I couldn't say no, staying out of management. I've always felt if I got the management, then that would be the curtains for my research, and that course was what I was most interested in. And so I, first of all, told Bruce and Darrell, no, I don't, that's not really a high interest to me. And they said, well, no, you know, people are looking at you and thinking you would be a good person to fill some of these positions. And I guess that gave me confidence that perhaps I could do some, be useful in that regard. And so later on, when they came back to me and asked me to run for election as the division chair later on, a few years, then I was a little bit more receptive and said, okay, that would be fine. And as a consequence, I became the division chair for 3 years. And in that capacity, I'm sitting on the board of directors at TMS. And that was interesting from a completely different viewpoint, that here there are people from all the divisions. These are real experts in their particular fields, and we had to work together to some common purpose. And sometimes there wasn't apparent a common purpose, but we could always find it, and at the same time think about what is best for TMS in this activity. So that was a lot of fun. I'm doing this, of course, simultaneous with my normal research activity, and then my involvement with the NNI there for a while, and in addition to my outreach type activities we'll get to later. So I, as my wife told me many times, you don't know how to say no. You keep on taking on these new activities, but you got to give up something sooner or later. And many years later, I did take her advice, and I did start to give up a few things, but I still have that problem in any case.
You eventually, you know, became president of TMS, and that must be a really big job. What was what was that like?
So yeah, so I became voted as a nominee, and then voted in as president of TMS in 2007. But I was voted in as vice president a year before then. And I actually sat on the board of directors a year before that. In order for me to serve in that sort of position, being a government employee, I had to get permission from my management to do that. Even though, with my discussion before I agreed to other people nominating me for that position, they all told me, especially previous presidents that I would query, they, without exception, says, "Oh, it's a piece of cake. There's not any more work involved in this at all." Well, they lied to me. And in fact, I think I probably lied to others after me, my presidency, because if you told the truth, they would not accept the nomination, I'm convinced. At any rate, as a government employee, I'm not allowed to serve in a position, leadership position like president of the society during government time. The only, with one exception, I could be in the administrative position in the American Institute of Standards, being a metrology entity. I would be allowed to serve in that position on government time, but any other society I belong to, especially in an administrative position, I could not. So I talked to my administrative superiors at this point and told them I would be happy to do this on personal time, this activity. That is, I would take leave anytime I went on to a meeting specifically for TMS specifically, and or was spending time at other times focused only on TMS activities. So I figured I could work on the TMS presidential duties perhaps one day a week, and the rest of the time, no problem. Well, things like these presidential duties aren't all coming to you on that one day a week. They're coming at you all the time. So basically, I would take leave for approximately the same amount of time in a whole week, but I would be having constantly to pick up a phone and call somebody, or receive a call from somebody, or answer an email, put together a letter, whatever, quite a bit of time. And then I could go back to my research. So I managed to do that. And but obviously I got the okay of my management for me to then be nominated for this position on the basis that I would use my personal leave for times I was focusing only on TMS activities. And in fact, I used up pretty much all my leave, which I had been accumulating for years anyway, during that time. But it was very enjoyable. I look back on it. There are two things which I really look back on as being successes. One is I was really interested in getting more interaction between the various professional societies. And so one of the things that I was pushing, and luckily was successful in, many things I was pushing weren't successful in, but the one thing that was successful was to join into a partnership with the Materials Research Society, MRS, in sponsoring this government fellowship for a member of our societies to spend a year down as an intern on the Capitol Hill, working with some senator or a congressperson or a major committee down there. And the stipend for supporting this intern would be coming from combined half and half TMS and MRS. So I was really happy to see this congressional fellowship get started. And secondly, to establish this interaction with the MRS, hoping it would blossom out into more and more interactions, and specifically try to get joint student chapters between the societies. That unfortunately never happened. It turned out to be more problems than we could solve at that time, and so that never happened. Second thing I got started, and it's only partially successful, was to get since I was very active in STEM activities for many years before this and many years afterwards, I realized that if we could partnership a professional society with um, other organizations around the country which have a focus on educating our youth, that we could expand the amount of science education to our nation's youth. And specifically, I had found that the 4-H organization, which is the educational arm of the Agricultural Extension Service of the Department of the Interior, Agriculture, and they have obviously a focus on education, but they don't have the expertise in educating youth in the sciences other than animal science and food science. Well, if we could partner them with a professional scientific society like TMS, then in principle, we would be able to help start STEM activities throughout the nation, since there are 4-H agents in every county of every state of the U.S. That only worked partially. We got something really going in Maryland between the 4-H organization and materials chapters at the University of Maryland specifically to get something going there. We had something going on already in our local area here in Maryland, and we're still working to expand that even further. So indeed, I think that getting involved in the professional society one should really do, and the payoff will be wonderful.
So Bob, I really enjoyed the times that I came out and worked with you on the Adventures in Science, that 4-H, education activity for a whole decade when I was living in the DC area. That was a really great program. What other types of things have you been working on that are kind of outreach activities to try and engage students in science and technology?
I've been involved in a lot of outreach activities, probably starting early 1980s. So shortly after arriving in the Washington, D.C. area, when I joined the National Bureau of Standards, I noticed that my children, actually it was before my children got into school, but noticed that there was not a large emphasis in science education. I actually met up with a fellow named Ralph R. Nash. He was a retired NASA scientist. In fact, he was a material scientist, interestingly enough. But he went by his middle name, Robert or Bob. And he had noticed that with his children who were in the school system here in Montgomery County, which was one of the supposedly more advanced public educational areas, that his daughter in particular was not getting a very good introduction to the sciences. And so he started something in his basement. This was in 1973, and so well before I got to the area. And this is the program you were mentioning that you then participated in for a number of years. Wonderfully, I might add, your sessions on magnetism were a favorite of a lot of the students, as well as mine, because I knew what you were doing before you did it, and you did a wonderful job putting together a nice sequence of things for the kids to do. But so in 1973, Bob Nash recognized there was a need to do something outside of the school system. And so he started this program called Adventure in Science that you alluded to in his basement on Saturday mornings for local neighborhood children. And so I think the first year he started, there were like 8 children. They would meet in his basement for a couple hours, and he would go through some sort of scientific activity. Being from NASA, he had a particular focus in astronomy, and so he would lead hands-on type activities for these children. And that was kind of a key of his, and I would say it was very foresighted of him to recognize there was a need to develop a program like this so long ago, before it was widely recognized that our nation was going to have a problem with scientifically educated population. And so I found out about it. Well, after a while, it outgrew his basement. So I read an article in the local newspaper. That's how I found out about this program, and then called up Bob Nash and talked to him a while. Even though my children were too young at this time to participate in, I was interested in perhaps helping out. And of course, he was always looking for volunteers. And so I started to lead some sessions on metals, and I think on friction, I think was one of the things, and heat conductivity was another topic I led. Initially in his basement, but then by the time I got there in 1980, a fellow named Tom Charlton had started a site of this program at NBS, where I was working. So in fact, I met Tom, and then much of my teaching was actually at the NBS site. Then I think like in 1985, Tom got a job elsewhere up in Connecticut. And so he left NBS, and the future of this program or site at NBS was really up in the air. And Bob Nash called the parents and a lot of the children. By this time, my son was involved in the program, so Bob called the parents of the children that were in the program together who worked at NBS to see who would be willing to take it over and help lead it. So I agreed to do it with 3 other people. So not by myself, but with 3 other people, and had the program continuing after Tom Charlton left. And I then continued to lead the program up until I think maybe 2000 and I think maybe it was 2001, something like that. And then I continued helping lead the program, but somebody else was more the principal person while I became president of the whole organization. And when Bob Nash decided to retire from the area and actually moved up to Maine to be closer to where his daughter was living at the time. And so this program grew. When I joined it, there were probably 30 to 40 children involved, maybe 50 children total. We started sites at the Hewlett Packard Corporation, and at Lockheed Martin Corporation, and at Bechtel Corporation, and at IBM at different times. And then over time, one would close down because the company was moving out of the area, or the people who were leading it were leaving the area, whatever. So we're constantly moving from one place to another. But we always had a number of different sites we got going for these hands-on activities, which would run from October of one year, every Saturday morning pretty much, except for the holiday periods, until March the following year. And we would typically have 150 to 200 children. Now, for the last 10 years, I think we've had well over 300 children involved in the program each year. So we've had a lot of children come through the program, and by and large have had positive experiences. And, and that was one of the objectives of this program, was to try to address children early. So we would start at age 8 and go up to age 14, so pre-high school. After they got to high school, then we generally, there were things available in the high school for them to get involved in. In some cases, some of them would still stay with us and help act as teachers or additional pair of hands. But the things that we wanted to do was to teach the scientific method to children in general, not for the purpose of them becoming scientists necessarily, but at least so they can answer questions of a scientific nature themselves. They don't need to go to Matt Willard or Bob Shull to give them the answer to the question they will pose, but to give them the tools to come up with the answer, figure out the answer on their own. And but also the second thing was to expose these children to as many different topical areas as possible. So each Saturday morning, the children at the NBS or the NIST site, they'd choose one of maybe 5 topical areas where there'd be somebody like myself or you, Matt, leading that topical area. And they would spend 2 hours learning basic concepts in those areas. And then the following Saturday, they would be presented another 5 different topical areas they could choose from to participate in and learn in. So in the 21 weeks that we were working with them each year, children would learn lots of different topical areas, so with the hope that they would find an area that really excited them and they might want to go into much more depth in the future, learning much more about that area, perhaps even end up working in those areas. So that was the second objective. And the third objective was to make these teaching sessions fun. So the children would be actively participating in them. They were hands-on type activities, so the children were not passively just seeing and listening to somebody, but they were actively doing something, performing some experiment, whatever, while we would be walking around lecturing to them without them realizing it. And of course, when they would measure something or come out with some result, we'd go off on some tangent. Oh, well, you know what that means, and we go off into some tangent, bringing the child recognition of what they did to their real world of things that they do. And lastly, to teach them that science is not that hard as long as you know the basic concepts. And then you can start using the scientific method to probe answering questions that you're presented in the future. So that was the whole purpose of it. And indeed, we did join with the 4-H organization, a partnership back in year 2000, when the local leader of the 4-H organization saw this program we had and realized this is one way they could help expand their areas that they would address the local children in. And we saw the 4-H organization as a way of potentially expanding it. So that's the major activity I've been involved in, well, since 1980. So it's what now, almost 40, 50 years almost. I've been doing this every Saturday morning for basically 6 months. Area I got involved in was to provide internships for older children, specifically those who are now in college as undergraduates, to provide an internship at NBS, actually NIST by this time when I got it started, at NIST. And this came about from the fact that I would, a program called the SURF program, or Student Undergraduate Research Fellowship Program, was started at NIST by a scientist in our physics laboratory. He had gotten some money. He then applied for some money from the National Science Foundation for helping support this for 2 or 3 years, I guess 3 years. And during that time, he would come to me knowing that I many times would bring students in from my adventure and science program to actually work in my laboratory in the summertime. This fellow from our physics laboratory at NIST would come to me saying, well, you know, I've got a student who wants to do a materials project, or he wants to work in materials things, whereas all the projects they had were all physics based rather than materials. And so wanted to know if I would be interested in having them work in my laboratory, and I would usually say yes. And in at a meeting, a local meeting of actually not TMS, but the Materials Research Society, I met this young lady, Terrell Vanderoff, who was a ceramicist, at an outreach lecture during lunchtime once. And it turned out that she was going to be moving to Maryland, and she was going to be joining the National Institute of Standards and Technology in our ceramics division. So of course I became really interested in getting to know her better because she was interested in STEM type things. And so not long after she came to NIST, we decided that we would go to the National Science Foundation ourselves and see if we could get a grant to expand this SURF program beyond just this one laboratory at NIST into making it into a bigger program. And we were successful getting that grant. And so we joined with the physics department laboratory at NIST and had this SURF program that was joint. That we then began contacting the laboratory directors of the other 5 laboratories at NIST to see if we could get the program started there. And so one by one, Terrell and I, along with the 2 people who were leading the physics laboratory part, managed to bring all the laboratories at NIST on board to having their own activity kind of jointly with it. And so that has become, again, a very, very successful program. We started out with, I think, 10 students in our material science program that joined the 10 students in the physics lab program, and which had been started a couple of years before ours, as I mentioned. And now there's like, I think, 200 students who come to NIST and spend the summer there. And it's interesting to hear management now refer to this program as one of their best programs that they have going on there, because they create all these ambassadors for NIST who, after the summer there, they go out and they advertise what NIST and what a great place NIST is, and the great things that NIST scientists are working on, et cetera. So it's been a great public relations activity for NIST, which of course they didn't think about initially when this grassroots activity got started.
Well, thank you for sharing your stories about the outreach efforts. Quite remarkable. A lot of growth, and in a really important area, really needed nationwide, really. But it's good that it's taken root very deeply in Maryland. I wanted to as we get close to the end of the interview, I was hoping that maybe you could share your father's Nobel Prize. I know you have the Nobel Prize someplace because I've seen it before. Do you have it with you now?
Yes, I have not lost it, and I actually do have it here. So I'd be very happy to share it with you.
Can you show it to the camera here?
Oh, you want me to show it to everybody else?
Please.
Oh, I thought you just wanted to see it personally. Okay, yes, of course. So here it is. So this is the the front of the metal, or in this case, it was obviously my father received it in physics. He received it with Bert Brockhaus for pioneering the area of neutron scattering specifically. And on the back of it, it has, of course, the front of it was the relief of Alfred Nobel, who started this prize. And on the back, there are a couple muses in this case. Each discipline, by the way, of the Nobel Prize has a different arrangement on the back of the medal. On the very bottom, then my father's name is inscribed along with the year in Roman numerals that he received this prize in. It's where there is not relief of these muses, the other areas are quite flat and smooth. And similarly on the front side, similarly on these areas where the relief is not present, it's nice and smooth. And that's quite different than the Nobel Peace Prize medal. Those areas are very rough, in fact. And that's how you can distinguish between the medals from the Nobel Peace Prize from these medals, which are awarded and handed out in Sweden in the sciences and literature and medicine. So there we go.
Fascinating. Thank you for showing that. I'd like to ask you maybe a more personal question about your relationship with your father. I hope you don't mind me asking, but I've always wondered if you felt any pressure to match your father's scientific achievements, and maybe get your own Nobel Prize, to match the one that you just showed us. Did you ever feel that type of pressure?
No, I did not. I think it's common for I think a child of somebody who has achieved some real significant thing, for them to feel pressure to match such accomplishments. In my particular case, I did not, and the reason is twofold. One is, by the time that my father was awarded this prize, I was already, 1994, I was already well established, as we've described in this video before now, in my own fields, and which were somewhat linked to the field of my father, in the sense that I did use neutron scattering as a tool for some of my work, but different enough that I wasn't competing or in the same area. So that was one reason that I did not feel so much pressure. And the other thing is that I figured if it took 50 years from the time that my father did his very formative work, so that was the same year I was born, basically 1946, is when my father joined went down to Oak Ridge, Tennessee, and 1994 when the prize was awarded. So if it takes 50 years for that prize to be awarded, that means that for me, I would have had to have already done the significant work, the earliest significant work, well before then. And so there was no pressure for me to match it to get my own Nobel Prize. Although I did note that if looking at the numbers of people who received the Nobel Prize since 1900, when they first started awarding it, whose parent also had received the Nobel Prize, that looking at the proportion therein, I noticed that my chances of receiving the prize went from absolute zero beforehand, before 1994, to a whopping 2.5% afterwards. So maybe that's been an oversight that my name hasn't been announced since 1994, but I'm sure it'll be corrected sometime in the future.
I'm glad those odds are on your side, Bob. Do you have further advice for students and young professionals that you'd like to give?
Well, I think I'm not sure if I have any further advice now, but the one thing that I've said before, and I'll reiterate it here in closing, is that get involved in your professional society. I've benefited significantly by having been a member of especially TMS, but I'm also a member of IEEE. In fact, I'm a fellow of IEEE. I helped actually put together the Nanotechnology Council for IEEE, but I'm also a member of the American Physical Society. I'm also a member of the American Society of Metals, and sometimes a member of the Materials Research Society. But the society I've spent most of my efforts and time has been TMS. And the reason for that is that the structure of TMS with respect to its parent society, AIME, which is, of course, sponsoring this oral history, is really the proper relationship. That is, the founder society, AIME, is made a decision many, many years ago that the member societies which came out of that founder society, TMS being one of them, AIME decided should be the stronger entity. That is, membership dues go to the member society, and then some of those will go to AIME. And of course, the member societies are closest to the members. So they have a much, much more direct connection with the membership, I think. If you compare that to a society like IEEE, it being the original society, and out of it spawned many member societies like the Magnetic Society, Electronic Society, etc. IEEE made the decision years and years ago that they would remain the stronger entity and that the member societies would be the weaker entity, which I think is the wrong format, because then even when once membership dues go to IEEE and then they disperse that to the member societies, IEEE, the parent society, can make decisions which are not necessary for the best interests of the members. So my advice is get involved in a professional society, and it makes no difference which one it is, really, even though I see differences between these different societies, and volunteer in them. And the payoff will be manyfold to you as a consequence of that.
That has certainly been the case for me too. So thank you for saying that. And thank you, Bob, for an enlightening conversation. And I really look forward to seeing you in person sometime soon instead of just on the computer.
So well, hopefully this pandemic will end soon, and
yeah, right.
we'll be able to actually get together in person at meetings, etc. But anyway, thank you, Matt, for putting together these questions to probe my career, and I thank AIME for hosting this, making it possible to share some of this information with the rest of its membership.